Ideal gas law errors. Okay, the ideal gas law, PV equals nRT, it works great when gases act like dots. Just points in space, no mass, no volume. They can't react, they can't collide. I mean, when you have those conditions, the ideal gas law gives you great answers. Well, it sounds like it's useless. Well, not really. When the temp is really high, gases are flying around so fast that, they're essentially acting like dots. When the pressure is very low, again, that really helps gas molecules act like dots in space. They're not going to interact because the pressure is so low. So high temperatures, low pressures, you get this dot action going on. And the ideal gas law, PV equals nRT, works great. However, not always working under those conditions, and you can have some pretty serious things happen. So science has come up with more equations than just the ideal gas law. We have the virial equation, van der Waals, Dieterici, Benedict-Webb, Rubin. So there's a lot of expressions that we've come up with for gases besides the ideal gas law. So how do we visualize the molecular motion of a single gas molecule? Check this out.
The path of one particle in a gas is very erratic. The particle will continuously change its course as a result of collisions with the walls of the container.
Notice that the gas molecule also traveled in straight lines. So here's an animation of the molecular motion of many gas molecules.
The paths of gas particles are very erratic. Particles continuously change direction and velocity as a result of collisions with other particles and with the walls of the container.
When the gas conditions are such that there's collisions among gases, there's gaseous reactions, we need to take into account that gases are not dots, okay? And that's where this theory is going to come in. We're going to talk about the kinetic molecular theory of gases. And it has several postulates, several main ideas. One is that gases are composed of molecules whose size is negligible compared to the distance between the molecules, so very extremely small particles. These molecules move in straight lines in all directions and over a range of speeds, but they have an average speed. Forces of attraction and repulsion between the gas molecules is negligible except when they collide. When gas molecules do collide, the collisions are elastic. What is an elastic collision? These are steel spheres, and those are elastic collisions. In an elastic collision, the energy does not go to deformation. Both before and after the collisions, the objects remain exactly the same shape. So where does the energy go then? The energy from an elastic collision gets dissipated through sound and heat. And I can illustrate the heat by burning holes in paper. So each time there was a collision, it burned a hole in the paper. The average kinetic energy, in other words, how fast a gas molecule is moving, is directly proportional to the temperature of the gas. So the higher the temperature of the gas, the higher the average speed of these gas molecules. And we've seen that before with liquid nitrogen and a balloon. Inside this balloon, it has air, and those air molecules are striking the inside surface of the balloon. And they're striking with such a force that they're pushing out the sides of the balloon. In fact, if I drew 1 square inch on this balloon, the air molecules inside the balloon are striking that square inch, and then the force that they're striking it in pounds would be the pressure inside that balloon. So what would happen if I made those air molecules cold? Well, I could put this balloon in a refrigerator, and it's actually going to shrink because the air molecules will start moving slower. But the balloon wouldn't shrink that much. I want to really slow down these air molecules so that the pressure that they create is even lower. What I'm going to use is liquid nitrogen. Now, if you cool air or nitrogen down to about 330 degrees Fahrenheit, below so negative 330 degrees, this is what it looks like. So if I pour this on this balloon, the balloon should definitely shrink because those air molecules are going to get very cold, they're going to slow down, and they're going to strike the surfaces, the inner surfaces of this balloon, with a much weaker force. Now what's interesting is when I stop pouring the liquid nitrogen, look what happens to the balloon. Instantly, when I stop pouring the liquid nitrogen, the air molecules are already starting to warm up and travel faster and increase their pressure. So the balloon goes back to its original size pretty much when you're at room temperature again. Get back to the original pressure. So here's 3 animation experiments. See if you can fill in the blanks for each of these experiments.
The ideal gas law relationship between pressure, temperature, volume, and number of atoms can be demonstrated using a piston. As the volume of the cylinder decreases under constant temperature and number of atoms, the pressure increases due to the increased rate of collisions against the wall of the cylinder. We now lock the piston to create a constant volume and number of atoms. Increasing the temperature results in increased kinetic energy for the atoms. The result is an increase in both temperature and pressure. Removing the heat source allows the kinetic energy of the atoms to dissipate to the surroundings, and the system returns to original conditions. With pressure and temperature held constant, additional atoms can be added to the cylinder. This results in an increased volume in the cylinder. If we double the number of atoms, the volume will double under these conditions.
I think a takeaway message for today's topic is not only to have a good feeling and understanding for the postulates of the kinetic molecular theory of gases, but also to realize that when the temp of the gas is really high and the pressure of the gas is really low, hey, we can get by using the ideal gas law. Because the molecular nature of this gas, of its composition, its size of the molecules, the mass of the molecules, is not important. They're acting like dots. So we can get by with the ideal gas law, PV equals nRT. If not, well, we better use a different law. And here's a bunch of them.